This video is the first of 3 short videos about multiplexing techniques. This first video is about frequency division multiplexing, or FDM. One of the oldest forms of multiplexing is frequency division multiplexing. From life experience, we are all familiar with this technique for legacy AM, FM, and analog TV broadcasting. Stations in these broadcasting services are assigned permanent frequencies of operation, commonly referred to as channels, in their various bands of operation. When we desire to listen to or watch a particular station, we tune our radio or TV to that particular station's frequency, as shown here in Figure 1. Of course, newer technology has started to change the situation. Eventually, multimedia streaming over the internet, radio and TV feeds might change our perception of this process. If we look at Figure 1, what we see is a single frequency transmitter with its sine wave generator and antenna. To the bottom right of that, we show the spectrum or frequency domain view of that transmitter output. It's a spike in the frequency domain. To the right, we see numerous spikes because there are numerous stations that broadcast wirelessly, we'll say. And what we see is the receiver to the far right has a tunable bandpass filter. What we can do is move that tunable bandpass filter around the frequency spectrum and choose or pick which signal out of many that we want to take and pick up. Here in the box in the middle, it turns out that we've chosen the middle spike, whatever that channel is. Today, the legacy broadcasting services, as well as many other over-the-air or wireless services, still use this technology to share the available frequency spectrum. However, this technique is not very efficient, and newer, more efficient techniques, for instance, CDMA, frequency hopping, and OFDMA, are being implemented for newer wireless services. The use of FDM is not limited to wireless services. For many years, AT&T and the Bell companies utilized FDM for their coaxial cable long-haul systems before adopting other newer technologies for these long-haul systems. Today, cable TV and DSL service use this technique or a variant of it to provide multiple TV signals and high-speed internet service over coaxial cable and copper pair transmission lines respectively. Today in the fiber optic cable realm, the use of wavelength division multiplexing, WDM, and dense wavelength division multiplexing, DWDM, are considered mature technologies. Despite the different names and associated acronyms used by the fiber optics industry, these technologies are just another implementation of FDM. Recently, the legacy analog broadcast services, AM and FM for instance, have all introduced newer passband modulation techniques to provide digital over-the-air transmission of their signals. Typically, to implement these high-definition versions of signals, they are employing some form of orthogonal FDM or OFDM. Again, these new technologies are but variants of FDM. So now I'm going to take and bring up Circuit Maker, and what we see here, this is the first circuit for FDM. I have 3 sources on the left hand side, V1, V2, and V3. They are all AM modulated signals, one at 10 kilohertz, one at 40, and one at 100 kilohertz. They're all applied to a 741 op-amp adder or summer circuit, and let's take a look. We'll run this and see what we get. So if we run this, let's take a look at this guy first. What we see is a spectrum of 3 transmissions. Located at 10 kilohertz in the far left is a AM transmission. We see the carrier and the lower and upper sideband. At 40 kilohertz we see another AM signal with a carrier at 40 kilohertz, a lower and upper sideband. And then at 100 kilohertz we see yet another AM signal with a carrier located at 100 kilohertz and a lower and upper sideband. In each case, you might notice that the sidebands are spaced at different frequencies from the carrier, and therefore they've been modulated with 3 different frequencies. If we take a look at the time domain representation of this, we see this signal. And very difficult to glean what the heck this is. One would be hard-pressed, unless you dealt with signals like this all day, to take and conclude that there are 3 AM modulated signals in this, but that's exactly what they are. So notice that the spectrum analyzer display, we can definitively see what's going on. With the time domain display, it's a little bit of a puzzle, to say the least. Okay, so let's stop this guy and let's go to the next file. So I'm going to open up FDM number 2 here. Open this guy up and make it a little bit bigger. Again, let's go to 150. Well, I tried to, didn't quite work it, so display. Let's go to 150. And now we have this diagram. And in this case, notice that V2 has become a different type of signal generator. V1's AM, V3's AM, V2 is FM. So let's take a look at what this looks like. We'll run it, and we'll take a look at this guy first, the spectrum. And now what we see is at 10 kilohertz I have an AM signal, at 100 kilohertz I've got an AM signal, but at 40 kilohertz I've got a FM signal. So it doesn't really matter whether the signals be AM or FM. They all get added together and form a composite spectrum out of the 741 op amp. Adding signals just takes and adds the different frequency components together. This slide just shows you what the frequency spectrum would be. If we go over to the other guy here, we take a look at this guy, and who knows what that is, but that's the algebraic sum of those 3 modulated waveforms, and you'd be really hard-pressed to tell me from a oscilloscope view here what the heck frequencies are in that signal. So again, the spectrum analyzer to the rescue. Let's stop this guy. Let's take and load the next one. This is FDM 3A. Going to open this guy up. Now you see a much larger circuit, and I don't know if I dare blow this guy up. Let's try it. Let's go to 150 again. Oops, maybe just be a little bit too big for the, yeah, so let's go to say 120. Okay, I think it just about all gets in there now. So what we have here is there are 3 waveforms, the original 3 signal generators, all AM modulators over on the left hand side, and they're added together by op amp U3, the first op amp, first 741 there. They are followed by, it appears, 2 op amp filters, and it turns out that in this case, let's run it and see what we get. So if I take and run it, taking a look at the spectrum, what we see is we have just picked out the 10 kilohertz signal. So this would be what we were talking about before with figure number 1. If we had a receiver and we want to choose the correct one, what we have to do is take and use some type of filter, and that filter may have been a low pass filter or a band pass filter, but we would take and reject the signal at 40 kilohertz. Now notice the filtering isn't perfect, because at 40 kilohertz you can still see a little bit of information there, and actually way out at 100 kilohertz you can still see a little bit of information. So one of the problems with radio receivers is that using filters that are, you know, based on L's and C's, inductors and capacitors, the bandpass characteristics of these things sometimes on the tails we can let some of the signal through. And you may have experienced that tuning an AM radio station, that you hear two stations at the same time. So let's take a look at, let's get over here and take a look at the oscilloscope display, and sure enough, here we have the 10 kilohertz AM wave. Looks like an AM wave, except there's a little bit of, if I take a look in between here, I see a little bit of noise, and it turns out that's probably the remnants of the 40 kilohertz and the 100 kilohertz signal adding in. So it's not totally clean, and we would, if we were trying to listen to the signal, we would, hear a little bit of distortion from those other signals that we have let in that we really don't want to have. So let's stop this guy. Let's take and look at the next circuit. So this is FDM 3B. Open this guy. And I don't think I'll blow this one up. We'll just leave it here. And in this case, what I've got is, again, my three signals on the far left. Let's see which one I choose this time. It appears that I now have put some bandpass filters in the output here. This op amp U1 and U2 form bandpass filters, and they filter the results of the adder here, U3. So let's take and run this guy, and what we discover is, now our bandpass filter has picked out the one at 40 kilohertz, but you might notice that there's still some signal down at 10 kilohertz, and there's still some signal over at 100 kilohertz. But we tried to choose this guy. Now, if you take a look at that AM signal at 40 kilohertz, you might notice that the lower and upper sideband are not symmetrical anymore. So what's happened is, again, my bandpass filter has affected the frequency components, and not in a good way in this case. Let's take and look at what the oscilloscope looks like. If we take a look at the oscilloscope signal, well, it looks like a 40 kilohertz signal. If we took and looked at the space in between these two peaks here, we'd probably see somewhere close to 40 kilohertz. But you might notice there's a bunch of junk here and over here and here between the signals, and that's probably more of the 10 and 100 kilohertz signals mixing in. But we've chosen the one that we wanted, basically. I'll stop this guy, and I'm guessing the last file would be one that chooses 100 kilohertz. Let's see if we're right about that. So we hit open, and we won't save anything. And here's our new filter, and again, it's a bandpass filter that follows the op amp here, U3. So I'm taking a run it, and sure enough, here's our. Now, if we take a look at this, centered at 100 kilohertz, we see we do have an AM signal, but we've taken and allowed a lot through of the 40 kilohertz signal. And again, what happens is the tails of a bandpass filter, both above the resonant frequency of the bandpass filter and below it, allow some of the signal through. So we have picked out our desired signal, the 100 kilohertz AM signal, but unfortunately we got some of the 40 in there. Let's take a look at what the oscilloscope shows us. Whoops, we didn't want to stop it. We want to go over here. And okay, so this one, we could see this guy here looks pretty good at the 100 kilohertz signal, but we see a lot of other junk in here, probably a lot of the 40 kilohertz mixing in. So it turns out that it's not very clean. We would desire to have a much better, sharper bandpass filter to just pick out that 100 kilohertz signal. Okay, that's for, again, the first form of multiplexing, frequency division multiplexing. It's been used for decades upon decades, and it turns out that it's the easiest, cheapest way to do things, but frequency spectrum is becoming more precious as time goes on, as we do more and more data communications, and so we've gone into some new modes of how we do things.